We're going to continue with stoichiometry today, and now we're actually going to get to see our stoichiometry calculations at work through dimensional analysis. So just a reminder, today we're doing mole-to-mole stoichiometry. It will get more complicated with our next learning target, but a reminder for what stoichiometry is. We're using a balance equation to calculate quantities needed for a chemical reaction. We'll also be calculating quantities that are produced in a chemical reaction. How we're going to do this is we're using a mole-to-mole ratio. Okay, now remember, when we were doing dimensional analysis and trying to find like the specific number of atoms or ions in a chemical reaction, we were using mole-to-mole ratios there, okay? We're going to be doing the same thing. Mole-to-mole ratios from a balanced equation, and those are going to function as our conversion factors. Now, what do I mean when I'm saying mole-to-mole ratios from an equation? Well, here's an equation. I have 4 moles of iron plus 3 moles of oxygen gas yields 2 moles of iron 3 oxide. All right? So how are we going to write our ratios? Well, if we're looking at just iron and oxygen, we can see that there's 4 moles of iron to every 3 moles of oxygen. 4 moles of iron to every 3 moles of oxygen. If we're looking instead at iron and iron 3 oxide, we have 4 moles of iron for every 2 moles of iron 3 oxide that's produced. 2 moles of iron 3 oxide. If we're looking instead at oxygen and iron 3 oxide, we have 3 moles of oxygen, right? So we're going to have 3 moles of oxygen. And how many moles of iron 3 oxide? Still 2 moles of iron 3 oxide. Once you have these ratios down, all this is going to take is simply plugging it in to an equation. So we can do ratios just between the reactants or between a reactant and a product. All right, so let's take a look at how we can put this into practice with our equations.
Okay. So, our first example, we're still going to use the same balanced chemical equation that Ms. Frankovic was using on the last page, and we're going to use, or on the last board, and we're going to use some of those mole-to-mole ratios and dimensional analysis to actually calculate how many moles of a reactant or product we need or get. So our first question, how many moles of oxygen gas are needed to react with 5.42 moles of iron? So we start out with our given, which is the part in the equation, 5.42 moles of iron right here. I put my moles of iron on top. I'm trying to get into moles of oxygen, so that is what I have on top. I put my moles of iron on bottom because that's what I'm trying to get out of. And then I use my mole-to-mole ratio that you just looked at on the last page. So what we are doing is we have 4 moles of iron and for every 3 moles of oxygen gas. So if I multiply across the top and divide by the bottom, first of all, my units cancel out, and I get 5.42 times 3 equals divided by 4, and I get 4.065 moles of oxygen gas, but I need to round to the correct number of sig figs based on my given, 1, 2, 3, so I get 4.07 moles of oxygen gas. So, if I start with 5.42 moles of iron, I am going to need at least 4.07 moles of oxygen gas to react to produce my iron 3 oxide. So now I'm going to figure out how many moles of iron 3 oxide would actually be produced if I had this much iron and this much oxygen gas. So, again, same given. So I start with 5.42 moles of iron. Set up my railroad tracks. Okay. Or my skeleton. On bottom, I have moles of iron. And I am trying to solve for moles of iron 3 oxide. So I put that on top. Iron 3 oxide. And then I go ahead and I figure out, using my balanced chemical equation, what my mole-to-mole ratio is. For every 4 moles of iron, I yield 2 moles of iron 3 oxide. So, if I go ahead and plug that into my calculator, 5.42 times 2 divided by 4 equals 2.71 moles of iron 3 oxide.
And what unit crosses out?
These guys, remember, cross out. So, it's exact. I look and I make sure that I still have 3 sig figs, I'm all good. So, overall, if I start out with 5.42 moles of iron, I'm going to use up 4.07 moles of oxygen gas, and we will end up with 2.71 moles of iron 3 oxide.
Right, so this will be very important, especially when you're thinking in terms of lab. This is really important for actually making chemical reactions happen that we want to. The next learning target will get more in depth here, so enjoy this more basic one.
Yeah. Next time we're going to be working on getting from moles of iron, maybe moles of iron, all the way out to how many grams of iron 3 oxide we would be producing. Or we can also do particles or anything else that we have from our mole island.
All right, that's it. See you next time.